All right, here's part 3 to our notes for the gas chapter. We've got a free response question from the 2009 AP Chemistry exam. The student was assigned the task of determining the molar mass of an unknown gas. They measured the mass of a sealed 843 milliliter rigid flask that contained dry air. The student then flushed the flask with the unknown gas, resealed it, measured the mass again. Both the air and the unknown gas were at 23 degrees C and 750 torr. The data for the experiment are shown in the table. So the first question is to calculate the mass in grams of the dry air that was in the sealed flask, and they give us the density. Well, the first part is easy. We need to get the mass, and that's just equal to the density times the volume. So I take my volume of 0.843 liters, my density of 1.18 grams per liter, which is given to us in part A, and I get 0.995 grams of dry air in the flask. You should be having your calculator in your hand and doing these calculations as well as writing them down. All right, part B, calculate the mass in grams of the sealed flask itself, i.e. if it had no air in it. All right, so we go back to the table and we see that the mass of the sealed flask and the dry air is 157.7 grams. And we subtract from that the air that we calculated in part A, and we get the mass of the empty flask, 156.71. Now, if this seems trivial or easy, the free response questions are structured to lead you down the road to tell you how to calculate all the things they want you to do. All right, step C, calculate the mass in grams of the unknown gas that was added to the sealed flask. All right, so the mass of the unknown plus the flask itself, 158.08. The mass of the empty flask, which I've calculated in part B, 156.71. I take the difference, I get 1.37 grams. That's how much my unknown gas weighs, or what its mass is. Part D, calculate the value of the molar mass of this unknown gas, right? So we use the fact that N is equal to PV divided by RT. I know P, it's 750 torr divided by 760. That tells us a number of atmospheres. I do that because I like to use 0.08206 for my gas constant, but you don't have to do that. Multiply that by my volume, divide by the gas constant times the temperature of 296 Kelvin. I get 0.034252 moles. All right, now I need to get my molar mass. My molar mass is just the number of grams divided by the number of moles, and I end up getting 40.0 grams per mole. Could be any gas, or not any, could be a number of different gases, but in part E, the instructor tells the student that the unknown gas was carbon dioxide. They consult the periodic table and see that carbon dioxide's molar mass really is 44 grams per mole. So we want to calculate the percent error in our measurement. So percent error is an absolute value problem. We're only taking the difference. Percent error is neither positive nor negative. It's just a number. All right, so it's 44.0 minus 40, the value we got, divided by the accepted value of 44, and I get a 9.1% error. Now, this is typical on the exam. They'll give you a couple of scenarios and ask you to comment about whether this could be true or not, or why. So, occurrence 1, the flask was incompletely flushed with carbon dioxide, resulting in some dry air remaining in the flask. Could that have been a contributing factor to the error? And the answer is yes, because the dry air density is less than the carbon dioxide density, which would have brought the M value down. All right, occurrence 2, the temperature of the air was 23, but the temperature of the carbon dioxide was lower than the reported 23. And the answer to that, or the answer to would that be contributing to the error, the answer is no. Cold carbon dioxide is more dense, not less dense, than the warmer carbon dioxide, so the mass of the sample would have been too high. So this could not have been a contributing factor. All right, G, describe the steps of a lab method that the student could use to verify that the volume is indeed 843 milliliters. You don't have to do any calculations. You merely have to talk about how can we verify this volume. All right, a couple of methods. Method 1, measure the mass of the empty flask, fill it with a liquid of known density such as water, and reweigh it. Subtract to find the mass. Volume is equal to mass divided by density. Method 2, fill the container with water, pour off the contents into a graduated cylinder, and measure the volume. There are probably a couple of other methods, including a spill-off method where you immerse the flask in a filled container and measure the volume of liquid that spills over into a catch basin. Or if it's a perfectly round cylinder, which it probably isn't, you could measure the radius and then compute the volume based on the formula for the volume of a sphere. All right, one application of the ideal gas law is a situation involving stoichiometry. So the way an automobile airbag works is you have a chemical reaction that takes place to fill the airbag. It's the decomposition of sodium azide, NaN3, to produce sodium metal and nitrogen gas. The gas, of course, goes to fill the bladder, the canvas bag that protects you from getting killed. We need to calculate the volume of nitrogen gas produced at 25 C and 1.1 atmosphere from the complete decomposition of 75 grams. Well, I think you can see in order to do this, we've got to get the number of moles of sodium azide. So we first write down our correctly balanced reaction. We see 2 moles of sodium azide reacts to form 2 moles of sodium and 3 moles of nitrogen. So 75 grams divided by 65.02 grams per mole for sodium azide gives me 1.1535 moles. I'm carrying 5 sig figs until I get to the end, when clearly all I can get away with is 2 sig figs at the end. But let my calculator carry all the digits for me. I use my stoichiometry to convert moles of sodium azide to moles of nitrogen, and then I use PV equals nRT, rearrange for volume, and that's equal to nRT divided by my pressure. And when I fill it all in and get the correct number of sig figs, I get 38 liters. All right, section 6, Dalton's law, partial pressure. All right, Dalton's law says that the total pressure of a mixture of gases is equal to the sum of the individual pressures if the gases were by themselves. Okay? We want to write the expression for the mole fraction of a gas as defined in their book. Okay? Well, the mole fraction is this fancy, it looks like a fancy X. It is the Greek letter chi. In English, that's spelled C-H-I, and it is pronounced chi. Chi, for any gas, we're using component 1 in our case. It's the moles of compound 1 or component 1 divided by the total number of moles in the mixture, or you could just say that's equal to N, the number of moles of component 1 divided by the total number of moles. So how can you use the partial pressure of gas 1 in a gas mixture and the total pressure of the gas mixture to calculate the mole fraction? Okay, so I know that that P1 is equal to the mole fraction, or N1 over N total, times the total pressure. Well, N1 over N total, that's just chi 1. So I have P1 is equal to Chi1 times the total pressure. And if I want to move that around and solve for Chi, I get Chi is equal to P1 divided by total pressure, which is very similar to the expression when I use the number of moles. And this comes from the Avogadro's hypothesis. So you could either write it as P1 over P total or N1 over N total. Both of those give you the value of the mole fraction, or that fraction of the total that is component number 1. All right, a mixture contains equal masses of oxygen gas and helium gas. The total pressure is 2.70 atmospheres. What's the partial pressure of each gas? All right, let's just assume I have 32 grams. No reason to know that. We're just going to assume that because oxygen has a molar mass of 32 grams. So if I do that, I can see that I've got 1 mole of oxygen and helium has a molar mass of 4. So that tells me equal masses. I've got 32 grams of each gas, so I have 1 mole of oxygen, 8 moles of helium. So my Chi for oxygen is 1 over 9, and my Chi for helium is 8 over 9. So that tells me that my partial pressure, or my pressure of the oxygen, is 1/9 of 2.7 total pressure, 2.7 atmospheres, or 0.300 atmospheres. And the partial pressure of helium would be 8/9 of 2.7 atmospheres, which would be 2.400. I add those together, of course, I get 2.70 atmospheres. And note that the partial pressure of helium is equal to 8 times the partial pressure of oxygen, which is entirely consistent with our molar ratio. All right, in the diagram at the right, I've got 2 flasks. They're connected by a valve. The flask on the left contains 10 liters of hydrogen at a pressure of 3 atmospheres. The flask on the right contains 4 liters of methane at a pressure of 2 atmospheres. And we want to know the total pressure of the system after the valve is open. We assume that the temperature remains constant at 25 degrees C, and the volume in that little neck in between the flasks is negligible. All right, there's a couple of ways to do this. Method 1, we can use Boyle's law, and we get the pressure of each gas after we open the valve. So for hydrogen, P1V1 equals P2V2. I put in the numbers and I get a pressure of 2.143. Or if I wanted to stop the problem at this point, which I don't really, I would say 2.1 atmospheres from sig figs. For methane, I do the same problem. I use Boyle's law, plug in the numbers, I get pressure 2 is 0.5714 atmospheres. And if I total those 2 partial pressures, I get 2.71 atmospheres. Now, there's another way to do this. I could use PV equals nRT to find the number of moles of each gas, and then use the total moles, put it back into PV equals nRT, and solve for pressure. If you get your calculator and do this, you'll see that the number of moles of hydrogen is 1.227. The number of moles of methane is 0.327. So the total number of moles, I just add the 2 together, I get 1.554. I put that into PV equals nRT, noting that the total volume is 14 liters because I have a 10 and a 4. I plug all of that in, and again, I get 2.71 atmospheres, the same answer I got by doing Boyle's law. All right, we are going to stop here, even though there's a part of this problem that's left, and we will conclude in the next section or the next video.